Hard, soft, acid-base theory. This theory was an extension of your Lewis theory of acids and bases. Before we go to the actual HSAB theory, let's first talk about the origin or how this HSAB theory came to be. So in 1950s, some group of chemists organized or classified metals based on the stability of complexes that they can form. So they were able to classify metals into two groups. So we have the class A metals and the class B metals. Now, when you say class A metals, these are metals that form more stable complexes if the donor atom is the first member of the group in the periodic table. So, for example, group 15, so the first member there is nitrogen. So, class A metals would form more stable complexes with a molecule who's donating, who is donating a pair of electrons from a nitrogen atom compared with a molecule who is donating a pair of electrons from a phosphorus atom. Okay, the same goes for group 16 elements. So it's oxygen. The first member is oxygen. So class A metals will form more stable complexes with molecules that donates a pair of electrons from an oxygen atom compared with molecules that donates electrons from a sulfur atom. Meanwhile, we have the class B metals. Your class B metals form more stable complexes if the molecule donates an electron from a phosphorus atom or a molecule that donates electrons from a sulfur atom, as we see here. So for example, we have chromium 3 and cobalt 3 ions. These are class A metals. So these metal ions form stable complexes. For example, if you have ammonia and pH3, then their complex with ammonia is more stable than that of pH3. Meanwhile, you have the class B metals. Example is silver ion and platinum 2 ion. So they prefer phosphorus and sulfur donors over nitrogen and atom, which means that they will form more stable complexes with pH3 than with ammonia. Now, Pearson, who read about this electronic theory of acids and bases, organized the concept. So he gave labels to these acids and bases and something about their strength, the stability of the complex that they form when they react together. And that is how your hard soft acid base theory came about, or the HSAB theory. So, according to Pearson, according to his organized thoughts, you have the soft bases, and they are characterized as having high polarizability, low electronegativity, low energy, HOMO or highest occupied molecular orbital, and they are easily oxidizable. Meanwhile, hard bases have the opposite properties. So it means that for hard bases, you have low polarizability, high electronegativity, high energy HOMO, and not easy, not easily oxidizable. Meanwhile, you have your soft acids. They have low positive charge, large size, and low energy LUMO. And hard acids have the opposite properties. So they have high positive charge, small size, and high energy LUMO. So notice that when you look at bases, you need to look at the HOMO or the highest occupied molecular orbital because again, your Lewis base, they are the ones that will donate electrons. And the electrons that they will donate can be found in the highest occupied molecular orbital. Meanwhile, When you look at your Lewis acids, you should look at the LUMO, or the lowest unoccupied molecular orbital, because this is the orbital that will interact with the HOMO of your Lewis base. Now, here I will show you a video explaining polarizability so that we can understand this concept further.
The second important factor is polarizability. Polarizability is the property that indicates how easily the electronic cloud around the molecule can be distorted to form an induced dipole. Larger molecules are more polarizable, since larger and more diffuse electron clouds are easier to distort. Therefore, larger molecules form induced dipoles more readily, and dispersion forces among them are stronger.
So that's polarizability. Again, if the molecule is large, it's more, or it's easier to polarize that molecule. And if you have a small molecule, it's relatively more difficult to polarize it, because again, your outermost electrons, they are the ones that will be distorted first. The outermost electrons in a small molecule still feel the attractive forces from the nucleus. Compared with a larger molecule, the outermost electrons don't feel, or probably they feel only a very, very tiny attractive force from the nucleus. That is why they can easily be distorted compared to the outermost electrons of a smaller molecule. So here are some examples of hard and soft bases. So you have their small ions like your hydroxide, water molecule, fluoride ions, etc. And you also have examples of soft bases. And we also have some borderline bases here, meaning like sometimes they can exhibit hard basic properties, or sometimes they can also display soft basic properties. And we have examples of hard and soft acids, and also you have your borderline acids here. Now, again, we know that your acids and bases react, but under the HSAB theory, there is a rule of thumb. So an acid and a base with similar electronic character interact favorably. So it means that hard acid, hard base, and soft acid, soft base interactions are preferred. So if you have a hard acid and a hard base interaction, they are interacting in the same way as your ions or polar species. It's because, remember, your hard acids, they have um, high positive charge, and your hard bases have high electronegativities. It means that it's the same way as your ions, such as your sodium ion and fluoride ion, for example, or in the same way as your polar species, such as water molecule and ammonia, for example. On the other hand, your soft acid soft base interaction, this one can be described in a similar way as a covalent bond. So it's because you have two large molecules, the acid and the base. They are easily polarizable. You can polarize them easily, which means that the outermost electrons can distort freely. They can distort themselves freely, and they can form the covalent bond easily compared to that of a hard acid, hard base interaction. Now, the thing is, the rule of thumb doesn't say that um, a hard acid, soft base, or a soft acid, hard base interaction does not happen. They happen as well. But in terms of probability or stability, your hard acid, hard base, and soft acid, soft base interactions, the products of these interactions are more stable compared to the products of your hard acid, soft base, or soft acid, hard base interactions. You might heard of the symbiotic effect from biology. This is different in your HSAB theory. So we have the term symbiotic effect in HSAB theory, but it's different. Okay, so a species behavior alone, meaning by itself, can be different if it is complex with other species. So, for example, if you have a species that is classified as a hard by itself, it can actually behave as soft when surrounded by a different ligand. So, an example for this one would be your cobalt 3 ion. So, your cobalt 3 ion is classified as a hard acid. By itself, it's a hard acid. But cobalt 3 can actually form a complex with 5 ammonia molecules. Ammonia molecule is a soft base. So notice that you have a hard acid and a soft base interaction. You still have a product. But again, the stability, so it's not that very high, but you still form this species. So you have this pentaamine cobalt 3 complex. Okay. So once you have this, cobalt here now acts as a soft acid. So it's now a soft acid. So it's like the interaction of your ammonia molecules. So the formation of 5 coordinate covalent bonds and producing this adduct somehow softened the character of your cobalt 3 ion. So there was a softening effect. So if you add, for example, either iodide ion or fluoride ion, okay, if you only knew that cobalt 3 is if you know only the fact that cobalt 3 is a hard acid, then you will answer uh, fluorine, like fluoride, like it will interact with fluoride. But actually, there is a symbiotic effect. So cobalt with this in this complex now acts as a soft acid. So instead of interacting with fluoride ion, it will actually interact with the iodide ion, forming another complex. So it's a pentaamine iodo cobalt 3. Cobalt 3 ion. We have NH3, 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 and then lastly you have iodine there, and the charge is now positive 2. So the charge, the net charge. Okay? So this is the symbiotic effect. Now, in the next video, we will apply the HSAB theory in some of the phenomena in chemistry that we are familiar with.